What's up, everyone? We're starting chapter 9 today, and this is a chapter on exponential and logarithmic functions. Here in 9.1, we're just going to look at what the graph of an exponential function looks like, as well as how to solve some basic exponential equations. All right, let's actually start with a little bit of an investigation. All right, we're going to open up this GeoGebra site here, and this applet, it's displaying the graph of an exponential function whose form is f of x equals c times a to the power of kx added with d. All right. So x is your input variable here, f of x, or y is your output. So that means c, a, k, and d. These are all parameters that I can change the values of. So I have sliders in this applet to do so. Right now, notice where the sliders are at. C is 1, A is 2, K is 1, D is 0. So that really means I'm looking at the graph right now of f of x equals 2 to the power of x. All right. A couple key characteristics of this graph. Notice the curve, the black curve, it's approaching the x-axis. It's kind of hard to see, but notice how the x-axis actually has a red dashed line on it. That's because we're considering that line, that horizontal x-axis, to be an asymptote to our curve. Asymptotes are lines that your curve approaches. They get infinitely close to the asymptote, but the curve never actually touches it. Okay. So we have y equals 0 or the x-axis as our asymptote. Also notice this curve has a y-intercept at 1, and it's increasing right now, meaning as you move from left to right on the curve, your curve is heading upward. Your y values are continuing to increase. Okay. Below the applet, I have some questions here. So question 1, how does the parameter a affect the graph of the exponential function? Okay, so what happens when a is greater than 1? What happens when a is less than 1? Right now, a is greater than 1. As I continue to increase the value of a, the curve just continues to get steeper. Okay, as I decrease the value of a and I get to be smaller than 1, notice the curve starts to decrease. Okay, and then the slider only allows me to go down to an a value of 0. It doesn't let me go into the negative. So that's an important property, that a has to be larger than 0. All right, so what we're seeing is that when a is between 0 and 1, the curve's decreasing. When it's larger than 1, the curve is increasing. But notice no matter what, the y-intercept is at 1 right now, and that asymptote is still at y equals 0, the x-axis. Okay. All right, so let's try to move that back to 2. All right. Question 2, how does the parameter k affect the graph? All right, well, at first glance, k is going to appear to have kind of a similar effect as the value of a, but notice that k is allowing me to use negative values. So it's when k is negative that the curve is decreasing, and when k is positive that the curve is increasing. Okay. Really what k is doing is it's having a horizontal stretch or compressing effect on the curve. All right. Question 3, what does the parameter d do to the graph? All right. Well, d is the number that's being added or subtracted at the end of the function. And notice that value determines your asymptote. Okay, whatever the value of d is, that's where your asymptote is taking place. Okay, and then last question. Suppose a is less than 1. Given this constraint, is it possible to get the graph of this function to look the way it does when a is greater than 1 and when k is greater than 0? All right, so a is greater than 1, k is greater than 0. I have that situation on the screen right now. basically we're focusing on the fact that the curve is increasing, okay? When we make a less than 1, the curve switches to decreasing, right? So the question is, that's being posed is, how can I make this curve look increasing if I keep a less than 0? And the answer to that is you need to make k negative, all right? So if you, that's based on properties of exponents. If you take a number between 0 and 1 and you raise it to a negative power, the result is actually going to be a number larger than 1, and it's going to have this increasing effect on the curve, okay? All right, so let's go back to the notes here, and in our first example, we're just asked to graph the function f of x equals 2x minus 1, all right? And then from there, state the domain and the range. So first thing I think to focus on is the number that's being added or subtracted at the end of the function here. Remember, we just saw in the illustration that that number determines where your asymptote is for the curve, okay? I'm going to say my asymptote is the horizontal line of y equals negative 1. And I'm going to, let's zoom in here, and I'm going to draw a dashed line to represent that asymptote, okay? All right, so now I'm just going to simply graph this function by making a table, right? And I'm just going to choose 2 negative values for x, 0, and then 2 positive values for x, all right? So f of negative 2, that would be 2 to the power of negative 2 subtracted by 1. Recall, raising something to a negative power can be thought as raising to a positive power if you just put it underneath 1. So really I'm working with 1/4 minus 1 here, which is negative 0.75. Okay, so let's plot that point. Just kind of estimate its location. All right, f of negative 1 would be 2 to the negative first subtracted by 1. That's going to be the same as 1/2 subtracted by 1, or negative 0.5. Once again, just estimate the location of that point. Okay, f of 0 would be 2 to the 0 power subtracted by 1. Remember, any number raised to the 0 power is 1. 1 minus 1 is 0. So we're passing through the origin. Okay. And then I think we can do the other two very quickly. 2 to the first power is 2. 2 minus 1 is 1. 2 to the second power is 4. 4 minus 1 gives me 3. And you could plug some more values in, right? If I went to an x value of 3, 2 to the third power is 8. 8 minus 1 gives me 7. Okay, so we've got plenty of points now to sketch this curve, and it's going to look like this. Domain for this is all real numbers. I can plug any value in for x, and I'll be able to get a result out for y. The range, however, is going to be based off of that asymptote. All right, I'm going to say that y is got to be greater than negative 1 in this case, or that's negative 1 to infinity in interval notation. All right, so now it's your turn. Pause the video, try to graph the function on the next slide here, and do so by making a table of values. And then when you're done, come back and check your work with mine.